Good evening, sir.
I've heard of lag, but this was too bad. Yeah, good evening, man. Thank you for confirming that I'm audible. Let's get started. So we stepped into week 5 today, right? And okay, week 1 was basically about representing data visualization. Weeks 2, 3 were primarily about descriptive analytics, chi-square goodness of fit test, chi-square test of independence. Week 4, we started off with modeling, basically a simple linear regression for modeling the demand response curve. And now we come into week 5, which is a bit of modeling and which a bit of prescription. All right. So you will have the nonlinear demand response curve. The nonlinear demand response curve. This is being introduced, which is a nonlinear model. Demand at price P is equal to C into P power minus epsilon. So this is the non-linear demand response curve. I'll not cover this during our course, but anyhow, then with constant elasticity, right? So that is this curve. And after this, we touch upon a topic in prescriptive analytics, which is basically optimization, right? So this is the main focus of week 5. Not me to just note taker. So this is the focus of week 5.
Sir, we will cover
Everyone with me?
week 5,
Ah,
sir, today.
yeah, we'll be covering week 5 today. Yes.
Okay, sir.
All right. So with that in mind, we are looking at optimization, right? Okay. So let's take this problem for example, which I've given to you on the screen. This is a past. This is a problem from a past QP. So you will have it in one of those QPs as well, and we will solve this in today's class. Right. So this is the problem. So what are you asked to solve in this question? What are you asked? Why would this question be of interest to a business?
Sir, can you repeat the question?
My question is, for the text that you see on screen, this text, this is a business problem. Why is it an important business problem? Yes, Bhumika.
Sir, sorry to interrupt you and disturb you. Sir, are we discussing week 5?
Yes, we are discussing week 5.
Sir, so when the TA session for the PYQs will be there?
That will be tomorrow. It is there in your
O-
calendar. Yes.
Okay, thank you, sir.
Mm. Okay. So this is the business problem. All right, fine. I'll proceed. I believe most of you are here for the wanting week 1 to week 4 revision. But anyhow, that will be done by the TS tomorrow. I will just start off with this. Any questions you have, you guys answer me. All right. So this is the business problem that any manufacturer would want to know how many items he can produce. Basically, cars and dolls he can produce so that he can maximize his profit, and this he has to do under the condition that he has only a certain amount of raw materials, right? So this is why it's a prescription problem. It is a prescription because you are going to tell how many cars to make, you are going to give this answer, then you are going to tell how many dolls to make. Because of these two questions which are there, and since you are going to give answer specifically these two questions under all the parameters that is mentioned in the problem, this is known as a prescriptive analytics problem. So all your optimization OR techniques are always prescriptive in nature because they hold true only as long as the business problems configurations are holding true, right? Sensitive analysis is there, but anyhow, predominantly the solution that you give is valid only for a certain environment on which it is proposed. So if the environment changes, the entire solution will change. So that is what it is. So to solve this problem, what we do is we formulate it as an optimization model. And to formulate anything as an optimization model, you need to know what type of a model you are going to build. And for this course, we are limiting it to a linear program, right? Why a linear program? Why is it linear? Because everything that we do is going to be a linear relationship. All aspects of the formulation are, or let me not say aspects, let me use the word all relationships. All relationships of the formulation are linear, basically degree 1. So when you create an optimization model where all the relationships are linear, it is known as a linear program. All right. So with that in mind, let's try to formulate this guy. So this is the problem. Right? Okay. So to formulate any linear program, there are 3 parts. The first one is the decision variables. The second is the objective function. The third are the constraints. And finally, the fourth one, which is some people call it as a subset of the constraint, some people call it alone. It is the non-negativity, right? So any linear program will have these 4 aspects. So what is the decision variable? The decision variable is nothing but what you want to find out. What is to be found, or the values of what is going to be found. That is going to be the decision variables that you take. In our case, it is going to be number of cars to make and number of dolls to make. Let's call this C, let's call this with the variable D. So that is your decision variable. What is the objective function? It is the target. we want to target or the goal we want to achieve. So in this problem, what is our goal? We want to make cars and dolls that can be sold so that we maximize the profit. So the objective is maximize profit. In this particular case, what are the constraints? The constraints are basically the physical characteristics of the problem, right? And what do these do? These basically establish bounds on the decision variables, which are the DVs. So you have DVs. I want to maximize profit. Make 100 cars, 100 dolls. You can say that, but that is not possible. Why? Because I have only certain amount of raw materials. So that limit on these decision variables is established by the constraints. They are the physical characteristics. And in our particular problem, they are basically the limits, or they are basically the limits imposed by the available raw materials. So there are two raw materials. So this would imply, since two raw materials, that means there will be two constraints for this specific problem, right? Finally, the non-negativity is a special type of constraint which establishes either the upper bound or lower bound for the DVs. Because this non-negative constraint is always like a particular DV is greater than or equal to 0. So this could either be the upper bound or lower bound based on what you are trying to solve, right? Or in fact, let's not even go to that much level. It's always going to establish the lower bound for the DV in our case. On the decision variables. So all decision variables must be greater than or equal to 0, which means the lowest value it can take is 0. And based on your constraint, they will always be moving up, based on which you will be ending up with maximizing your profit by identifying something for C and D. So these are the four aspects of a linear program. Now, looking at our particular thing, we can convert whatever we have written into numbers. So I've already told you the decision variables is number of cars, number of dolls. So the number of cars we are going to make and the number of dolls we are going to make are our decision variables. So C and D. What is my objective? My objective is to maximize profit. And what is maximize profit? It is nothing but maximize profit from car plus profit from doll. So what is the profit from car? Maximize. For every car that I sell, I get a profit of 5. For every doll that I sell, I get a profit of 4. So 5 if I sell one car, 4 if I sell one doll. How many am I going to sell? I'm going to sell C cars and D dolls. So 5C plus 4D. So this is going to be your objective function. All of you with me so far? Yes, no?
Yes.
Okay. So this is the objective function. So next what we have to do, decision variables done, objective is done. The constraints we have to write. So for this specific problem, if I have to make a car, right? For every car, I require 6 units of R1. For every doll, I need 1 unit of R1. So the availability of R1 and R2 are going to be my constraints, right? So constraint for R1 and constraint for R2. So there are going to be 2 constraints. So what do I say? I have only 24 units. So whatever I make must be less than or equal, must consume less than or equal to 24 units of R1. Similarly, whatever I make, since I have only 6 units of R2, it must consume less than or equal to 6. So that is your RHS. This is basically your RHS. This is the inequality, which is less than or equal to, and this is your LHS. So what is the LHS? I am going to make C cars and D dolls, correct? So for every car that I make, I need 6 units of R1. For every doll that I make, I need 1 unit of R1. So if I make C cars, 6 into C, R1s will be consumed. And if I make D dolls, D into 1, R1s will be consumed. And this total availability must be less than or equal to 24, which is this total consumption must be less than or equal to 24. So LHS is consumption, RHS is availability, consumption less than or equal to availability. Yes, no?
Yes.
Then can you tell me the next constraint? What is the next constraint?
Yes. 4C plus 2D.
4,
4C
4C plus
2D.
exactly. 2D must be less than or equal to 6.
Yeah.
So this is going to be your second constraint. Why? For every car that I make, I will consume 4 units of R2. For every doll that I will make, I will consume 2 units of R2. So if I make 4 C cars, 4 into C, plus D dolls, 2 into D, that must be less than or equal to what is available. So this is the formulation, LP formulation for this problem. The final one is the non-negativity, which is going to basically say non-negativity, which is going to basically say C must be greater than or equal to 0, D must be greater than or equal to 0. So this entire thing that we currently created is known as a linear program. Why? Because look at the objective function. 5C plus 4D. maximize this. This is linear in nature. This 5c plus 4d is of power 1. 1, 1, so power 1. Look at the constraint. 6c power 1, 1b power 1, 24 power 1. So everything is of power 1. Constraint number 2, 4c power 1, 2d power 1, 6 power 1. So everything is of power 1. Then non-negativity, c power 1 greater than or equal to 0, d power 1 greater than or equal to 0. So if you do this, everything that you created is having a linear relationship, and hence it is known as a linear program. Yes, no?
Yes.
Yes.
Super. Now let me ask you a question. Is it necessary that these constraints will always be of less than or equal to type? Can they also be of greater than or equal to type?
Sorry, can you please repeat the questions?
The question is, the constraints, should the inequality always be less than or equal to? Or can there be something else also?
Can be greater than equal to.
Give me an example. In the same problem, if I want a greater than or equal to constraint, tell me.
So if you have to minimize the cost of procurement.
Not necessary. No, then you are changing the objective. Right? With the same objective, and I have greater than or equal to constraint.
It's the same.
See, if we change the, instead of maximizing, if we are doing minimizing, that time that constant will be then change.
That is changing in the objective function. I don't want to change the objective function. Let's say I want to add one more constraint, and that constraint must be greater than or equal to. What will I do? How will the problem change?
Minus 6c minus 1b is greater than.
No, that is negative. All of this is mathematical operations. I am telling add a new constraint itself to the problem. The business can tell you some requirement. That requirement can be of the greater than or equal to type. Tell me one such requirement. Tell me some requirement like that. This is the problem, right? Let's say to this problem, I add one more statement. The toy manufacturer wants to ensure that at least
Minimum production.
cars are made. Let's say he gives you a minimum production requirement. Exactly, 2 cars are made. Then what will happen? A new constraint would be added to the problem.
C greater than equal to 2.
Yeah, so a new constraint, which is constraint for C, will get added to the problem, which will say C must be greater than or equal to 2. Now you see, this is a new constraint which is of the greater than or equal to type. So based on the problem and what is being told, your constraints can either be less than or equal to, greater than or equal to, or equal to. In the same problem, I can go and say, the toy manufacturer wants to ensure, let's say instead of this, he says this. The toy manufacturer wants to ensure he makes exactly one doll. Let's say he gives you this. Then what will happen? What will be the constraint that gets added?
B equal to 1.
Exactly. Constraint for D, D will be equal to 1. So this is how, based on what And look at all of these constraints. What are they imposing? They are imposing restrictions on C and D by capturing what? By capturing the physical characteristics of the problem. So physically, the problem says I have I have only 24 raw materials. Okay, then my decision variable should not consume more than 24 raw materials. I have to make at least 2 cars. Okay, then my decision variable must be greater than or equal to 2. I must make exactly 1 doll. Okay, then my decision variable for doll must be equal to 1. So any physical characteristic of the problem that is being imposed will always go and sit as the constraints in these constraints in this model. And the beauty of this is, whenever you have in a maximization problem, whenever you have a constraint of the type greater than or equal to, this non-negativity constraint becomes redundant. Right? It has no value. C greater than or equal to 0, C greater than or equal to 2. Obviously, this becomes a lower limit. Right? So whenever you have either a greater than or equal to or an equal to constraint, then in a maximization problem, the non-negativity becomes a redundant constraint. It has no meaning. Yes, no? All of you listening so far? Okay. Right. Let's go back to the original problem. So to this original problem, the formulation that we wrote in red, this formulation is known as the primal LP formulation. Right? I will come to why it's known as the primal in a bit, but this is known as the primal LP formulation. From this primal, we can create something known as the dual formulation. Right? Using the primal, we can create something known as the dual formulation. And while doing this conversion, what we insist in this course is that you make sure that the primal is in something known as the standard form. Or you can also consider this as the canonical form. Right? So whatever we refer to as canonical, standard form is the same meaning in this course, but there is a slight difference. We will not go into it. So either the standard form or the canonical form, whatever we say, we mean the same thing in this very beginner level course, and you must convert your primal to that form and then do the dual formulation. So what is a canonical? What is a standard form? In the standard form of the primal, the objective function must be a maximization. And then constraint. All constraints must be less than or equal to. So in any formalization, when the objective function is maximization and all constraints are less than or equal to, then it is known as the standard form. Or if you have an objective function which is minimization and all constraints.
Sir, what is this less than equal to 1?
Oh, sorry, my bad. Less than or equal to. My bad. RHS. Let me put it like that. Yeah, sorry, my bad. Standard form is this. This is also a standard form where objective function is minimization and all constraints must than or equal to RHS. So it has the standard form. And from the standard form, if you want to convert to a dual, you can use certain principles or certain shortcuts, right? To convert a primal in standard form to a dual, right? You can use these following principles. So in the primal, if the objective function is maximization, then in the dual, the objective function will be a minimization. Okay. Constraints. If in the primal, if it's in maximization, since it's in the standard form, it will be less than or equal to RHS. In the dual, it will become greater than or equal to RHS. Then, in the primal, what will be the objective function coefficients? Right? For example, in this formulation, the objective function coefficients are basically 5 and 4. This 5 and this 4. For every car that I sell, I'll make a profit of 5. For every doll that I sell, I'll make a profit of 4. That here, the objective function coefficients of the primal will become the RHS for constraints in the dual. And then the RHS values for the primal constraints these values 24, 6, right? These two values, they will become what? Can someone tell me?
Sense.
Exactly. This will become the objective function coefficients. What are we missing? One more rule that we're missing. This is rule number 1. This is rule number 2. Rule number 3. Rule number 4. There is one more rule number 5.
Number of constraints will become different.
Number of constraints in primal will become number of DVs in the dual. So that is also done. Okay. What will happen to the 6, 4, 1, 2? They will be the same, huh? What will happen to the 6, 4, 1, and 2? Okay, when I formulate it, you will see. Fine. So for this question,
It will get added in the objective function.
you will get
It will get added in the objective function for the dual, right?
how will they get added? Okay, fine. Let's formulate and see. So let's apply our rule. So we are going to create the formulation for this red, which is in standard form, because it's maximization less than or equal to. So all our requirements are met. So we are directly going to convert this to the dual. So what is the dual of this red box? First one, maximization will become minimization. What will be my how many decision variables I will have? I will have two decision variables. So R1 is one decision variable and R2 is another decision variable. What is going to be my coefficient? 24 and 6 will become 24 and 6 will become my coefficients. Okay. Then what is my constraint number 1? The constraint number 1 will correspond to the first decision variable, which is C. So must be less than or equal to 5. Sorry. Less than or equal. Did I write it here or did I forget? I wrote it. Greater than or equal to, no? So this is a less than or equal to constraint. It will become greater than or equal to, and the RHS value will come from the objective coefficient. So 5 and greater than or equal to 4. So this is going to be for C. This is going to be constraint for D, dolls. Now look at this. What are we telling? For C, I make profit of 5 by consuming what raw materials are. To make a C, I need 6 units of R1 and 4 units of R2. So 6 R1 plus 4 R2 must be greater than or equal to 5. Then 1 R1 plus 2 R2 must be greater than or equal to 4. The non-negativity stays as it is. The non-negativity stays as it is. So what are my decision variables here?
R1
R1 and R2. So R1 greater than or equal to 0, R2 greater than or equal to 0. So this is the shortcut for converting a primal to a dual. If it's a maximization, first convert it to standard form. So maximization, everything must be less than or equal to constraint. Once you have done that, maximize your maximization will become minimization. Your RHS will become your coefficients 24 and 6. Number of constraints will become the number of decision variables R1 and R2. Your constraints, the number of decision variables in the primal will be the number of constraints in the dual. If you want, you can also write it as a 0.6. Number of DVs in primal will be equal to number of constraints in dual. So I have two decision variables C and D. So I have two constraints, constraint 1, constraint 2, constraint 1 corresponding to C, constraint 2 corresponding to D. So what do I have? I make a profit of 5 for every car that I sell. So that 5 must be less than or equal to the amount of money I spend for making raw materials. So 6 R1 plus 4 R2 must be greater than or equal to 5. 1 R1 plus 2 R2 must be greater than or equal to 4. So the corresponding coefficients in the respective constraints for the particular decision variable C go into creating this. So this is the dual formulation. All of you with me so far? Yes, no?
Yes.
Yes.
I have only 4 people. All right. In fact, I don't even have 4 people. Only the 2 of you. Okay. Right. Everyone else dropped off. Okay. So now, can you tell me why is this known as the primal and this known as the dual? It could be that the dual becomes the primal and the primal becomes the dual. No. Why is the red one called the primal?
So because it is directly based on the business
Because
requirement.
it is. What is the business requirement?
So the maximizing the profit, right? So our objective function is made on the basis of that.
Beautiful. Yes. So any formulation which directly answers the question is the primal formulation. So our question was to maximize my profit. How many cars I should make, how many dolls I should make. Since my first formulation in red directly uses those as my decision variables, that is my primal. Okay. In that case, this this formulation which is in blue, for whom will it be the primal? What does it tell you? What does this blue formulation tell you?
Sir, when my goal will be to my objective function will be to minimize the resource requirement,
So for whom?
then
Let's say this primal formulation is for the marketing team of this business because
right.
they are for the production team of this business. However, similarly, for whom will this be the primal?
For the production team or for the workshop team, right? Sir? Because they have
Exactly.
specified the
So
amount of
for them, this would be the primal. So for the same problem, same characteristics of the problem, based on who is using it and what question he is asking, the corresponding dual and primal will come, right? And the most interesting thing here is primal. You have the primal. You can convert it to a dual, and when you convert the dual of the dual is basically the primal again, right? So this is the cyclic process. So primal, dual, the dual of the dual is again the primal. So we'll keep on circling here. Okay? Yes, no?
Sir, is it a combination of two constants in for that reason is it dual name or why that name is dual?
Oh, this is known as the dual because it is the inversion of the primal. No? Look at the primal. Maximization, minimization. Less than or equal to becomes greater than or equal to. So it is the inverse version. So it is known as the dual. And that is one way of looking at it. A second way of looking at it is the answer that this gives. The answers of the dual are basically the dual prices or shadow price for the primal. What do these mean? This basically tells you, let's say for this particular problem, okay? This particular problem, the solution that you are expected to get, what will be the solution? Can you tell me quickly? Any guesses?
the number of cars and the number of
What is it? Give me a number now. C is equal to what? D is equal to what?
um, equal to I'll just have to solve this.
It will be 1, 1. Because look at this constraint. So 4 into 1 is 4. 2 into 1 is 2. 4 plus 2, 6. It has reached. Substitute it. 5 plus 4, 9. The only other solution here is make this 0 and this 2. Two twos are 4. 4 less than or equal to 6. 2 fours are 8. 8 is always less than 9. So since I want to maximize, C is equal to 1, D is equal to 1 is going to be your optimal solution, basically. So at this optimal solution, okay, if you substitute, what happens? 6 into 1 plus 1 into 1 is equal to 7, which is less than or equal to 24. Then 4 into 1 plus 2 into 1 is equal to 6, which is equal to 6. These are the two values for the two constraints, correct? Yes, no?
Yes. Yes.
Oh.
Yes.
Now look at this beautiful case. Let's say a raw material supplier is coming to you. He is telling you, here, take a discount on R1, take more R1 from me. Will you buy? Will you buy R1? I am raw material supplier. I come and tell you, buy more R1 from me. Will you buy R1? Yes or no? I am coming you, telling you that I will give you more R1. Will you buy?
If it
No, you want.
means no, if it means
No. Because you are using only 7. You already have 24. Why do you want to buy more and keep? You will not keep. But if the same guy comes and tells you, I will give you R2, will you buy? Yes, you will, because if I get 2 more units of R2, I can make 1 more unit of doll and my profit will go up. So if he comes and gives you R2, you will buy. So this is known as a binding constraint. And this is known as a non-binding constraint. So what will happen is, whenever you solve the dual problem, the dual prices, basically these are known as dual prices, the dual prices or the values for the decision variables for those constraints which are binding will be non-zero. So binding constraint implies non-zero D price, which implies non-zero dV value in dual. Non-binding constraints are zero dual prices, because they are of no use for you, because that is not a binding constraint. You already have excess. So only for constraints which are binding, the corresponding decision variables for those constraints in the dual will be non-zero, and their values are known as the dual price. So those dual prices will tell you how much you are willing to pay, your willingness to pay to get that resource. So when I am the raw material supplier, I will formulate the same problem and I will find out what is your willingness to pay for R1, what is your willingness to pay for R2. That is why it is known as the dual formulation.
So
Yes,
basically,
no?
sir, the wherever like we are having a shadow price of a certain amount, so we can say that that particular resource has more value, right?
Correct.
Because
You are willing to pay up to that value to get that resource. In fact, that will also be quantified. If I get a shadow price of, let's say, 5, then you are willing to pay 5 rupees per unit for R1 to get that resource so that you can make a doll. Right? That is it quantifies. It not only tells you that you can buy, it also quantifies how much you are willing to pay. So that is why, as a raw material supplier, I will be interested. I can now come and quote a price for you. And if that price matches your dual price, which it should, then you will buy. If I quote more than that, you will not buy. Because it does not make sense. Because my profit, let's say I quote 5 rupees for a R2, right? Let's say I quote 5 rupees for an R2. You may not buy, because if I have to buy 2 R2, I will be able to make 1D, which means my profit is only 4. Making sense? So if you come and put me 5 rupees for R2, I will not buy. But if you come and put me 1 rupee for R2, I will buy. Because every 2 things I can increase by 4.
Yeah.
That is the beauty of it. It quantifies and tells you how much you will be willing to pay for that binding resource. Yes, no?
Yes, sir.
Right. And in fact, if you go into sensitivity analysis, it will go one step further. You can keep on increasing R2 only as long as you don't hit 24 here. Once you hit 24, both will become binding. Then the entire solution will change. That is sensitivity analysis, not in your scope, but that is what it is. And this is why it is a prescriptive problem, because for a specific setup, it prescribes the solution and tells for how long that solution that you are generating is valid. Beyond that, it will not be valid. Yes, no?
Yes, sir.
Okay. So this is the primary concept in week 5. I will stop here. It is quite heavy. Please go visit the videos again, because what I do is I start this lecture assuming that you have seen the videos. In case if you have not seen the videos, go revisit it now. A lot of these things will make sense.
Sir,
Okay?
I have a small question. So
Yeah.
actually, on the video, in one of the videos, like when the problem was being demonstrated, it was said that like the random variables, like the variables, so they are continuous with the code, but discrete, right?
When they become discrete, it becomes a new problem known as integer linear programming. Because where the decision variables must be integers. If it becomes that, right? If it becomes that, then it's a different ball game. The solution space itself changes, and all of that happens. So, since this is a very introductory course, we say that assume all variables are continuous. But if it is not, then it becomes integer linear programming. It could be binary. You could have only 1 or 0. That kind of problems are rare. Then it becomes a binary linear program. You could have binary and the integers. Then it becomes a mixed integer linear program, right? So there are several variations to this. But the basic one is a linear program. And all of these are variations to that linear program. We are not covering those.
Thank you. Sir, will the lecture, the YouTube link for the lecture be uploaded on the calendar?
YouTube, which lectures? These ones. These are there. No, these are already there in the YouTube channel. So you can directly go to the channel, and you can see there we have all of our lectures that are happening. These live lectures are over there. They will not be given in the calendar. It will be given in the YouTube channel.
So would you mind posting the link? I can't see the link.
1 second. YouTube. I don't know why it's not connecting. You are able to hear me, right?
Sorry, sir?
You are able to hear me, correct?
Yes, sir.
Yes, sir.
No, I don't know why, but it's telling no internet connection, and you lost your network connection trying to reconnect, and my YouTube and all is not opening. But I'm connected to the internet. Okay, let me do one thing. I will send it as an announcement, or else it should also be there in the discourse. Anyhow, I will send it as send it as an announcement to you, the YouTube channel link. Okay, so you can go and see it there.
On
No, it's
Discord,
not opening for me. That is all. That is why.
on Discord, right?
Oh, on Discord it's there. On Discord there is a pinned thread. It's all there. If it's not there, you can just post it as a request, and the TA will immediately give you the link. Or else I will send. I will tomorrow. I will go and send the this thing announcement saying that this is the link for the YouTube channel. That also I will do.
Announcement via the Discord, or
Huh?
announcement through Discord or Discord.
No, an announcement through this thing. The same announcement that you get when your content is released. You know, I will do that kind of announcement via email. It will come to you via email, registered DS email. Okay. But I will have to do that tomorrow because I don't know why this is telling no network.
Yeah, no problem.
Yeah. Okay, and there is a. Please check your calendar. There is a session by our TAs tomorrow where they will solve PYQs for your PYQs for your quiz 1. So you might want to attend that. That is between 7 to 9 tomorrow.
Okay, sir.
Thank you, sir.
All right. Yeah. Okay. So that is all from me. Thank you. All the best for your quiz 1.
Yeah,
Thank you,
thank
sir.
you.
Thank you, sir.